All right, in section 8.2, we are going to look at not only one vector, but two or more vectors where we're adding them together. This is important because if you think about a single object and you have multiple forces pulling on it, you might want to know what's going to happen to that object. So if I have three forces pulling on this box, which way will the box move? What way will it go? So we'll first look at a geometric way to add vectors, and then we'll look at a more algebraic way to do so as well. So one way to add vectors is to put the vectors head to tail. So if I have one vector, let's say it looks like this, we'll call this vector A, and then another vector, we'll call this vector B. So we put them head to tail, head of the first to the tail of the second. So once you place them head to tail, the sum of these two vectors is from the first tail, remember tail is the beginning, to the second head. And vectors can be moved around as you need, but if you have these two vectors head to tail, then this is your sum vector. This is the vector A plus B. Now that is one way to add vectors, not the most popular method. The most popular method to add vectors is what's called the parallelogram method. In the parallelogram method, you connect the vectors tail to tail. So you basically put them tail to tail, and this is a real popular method because this is how most vectors are, because they all start at the origin. So if you have two vectors that both start at the origin, they're already tail to tail. So then we can make a parallelogram, forming a parallelogram with these two vectors as sides. We'll have the sum as a diagonal. So let's go ahead and look at an example of this. So if I have vector C going this way and vector D going this way, then what I can do is I can use those two sides I have as the start of a parallelogram. And then the sum is just the diagonal that goes from those tails to the other side. So this would be vector C plus D. So say this is an object and you have one person pulling at force C, one pulling at force D, then the object would move along this green path, force vector C plus D. Another thing you can do is you can do what's called a scalar multiplication of a vector. And again, this is just when you multiply a vector by a number. Can be positive, can be negative. And let's just look at a couple different scalar multiplications of a vector. So let's call this little vector pointing this way vector A. Well, if I want vector 2A, then what happens is the vector just becomes twice as long. But the thing that doesn't change is its direction. You can also have a negative number. This would be -1 times the vector. And what changes when you multiply it by a negative, it actually goes the opposite direction. So that would be vector -A. I can also have a fraction. So if I do -half A, it goes the other direction and it is half as long. So these are all scalar representations multiplied by a vector. Sometimes you also want to subtract a vector, but when we subtract a vector, we really don't subtract, we're really just going to add the opposite. So if we want vector A minus B, we're really just making A plus the opposite of B, because we know opposite of B just goes the other way. So if we have vector A, let's say is this blue vector, and vector B is this vector pointing to the left, if I want to figure out what vector A minus B is, then I will just take vector A, which is going to be the blue one, and I'm just going to add it to the opposite of B. Well, the opposite of vector b would just point the other direction, so it'd be negative b. And then I could form my parallelogram, and so a minus b would be this vector here. So adding the opposite, because we know the opposite vector just goes the other way, is a really easy way to go. So if we look at this example here where we have these two vectors, they are already tail to tail, so it would be really, really simple just to go ahead and form our parallelogram. So we have vector u and vector v, and so vector u plus v would be this vector here, because we're just looking where the diagonal of that parallelogram formed by those two vectors are. Now, once you have the vector sum, you can do lots of things. You can find the magnitude, you can find the direction of that vector, anything else you want. Now, this is obviously a very geometric way to go with these vectors. An algebraic vector addition is sometimes a little easier way to go if you have the vector in component form. So if you have the vector in component form or position vector form, where you have the two parts of it, then adding them is very, very simple. Because all you have to do is if you have two vectors in component form, we'll just add their x components and their y components. So you just have to add the first numbers and the second numbers. Just that simple. So for example, if I have vector h, which is negative 5, 6, let's go ahead and draw this just so we get a kind of idea what it looks like. Negative 5, positive 6 would be a vector pointing this direction. So this is vector h. And vector k is negative 7, negative 9. So that's way down here. So that points down here. So we know the sum, if I was to do kind of an informal kind of look at what the sum vector is going to look like. Well, there's my parallelogram. So I'm guessing the sum is going to point somewhere down here. Now that's pretty rough, but I know it's going to be somewhere in quadrant 3 because it's left and down. And what you can see here is if I want vector h plus k algebraically, I'm just going to take the x components and add them together. So negative 5 plus negative 7. And then I'll add the y components together, which are 6 plus negative 9. Now if I add those two together, I get negative 12 and I get negative 3. So I would not doubt that this sum vector h plus k is negative 12, negative 3. So right away, I know what my sum is. So if you have it in component form, really, really simple to find the sum. So let's look at our next example. It says find the vector 2h minus 3k. So in this case, we have two vectors, but we really don't know what each of them are. So what we'll do is we'll find the vector 2h first, and we'll add it to the vector 3k. So remember the vector 2h, when you're multiplying a vector by a number, you're just multiplying both numbers in that vector by the number out front. So we're just doubling both of those numbers. So the vector 2h is going to be negative 10, 12, because we're just doubling the negative 5 and the 6. Vector negative 3k, we're going to multiply those both by negative 3. So that's going to be 21, and that's going to be 27. And so now that we have those vectors, we'll just go ahead and we'll add those two vectors together, which is just going to be add the x parts and add the y parts. So negative 10 plus 21 is 11. 12 plus 27 is 39. So that would be vector 2h minus 3k. So let's look at another example. Now in this case, we have two vectors. We want to add them together by finding components, and then we want to find the magnitude and direction of the vector. So if we graph this, vector A is going to kind of face the first quadrant, something like this. Vector B is negative 2, 9. So it looks something like this. So geometrically, the vector sum is going to look something like this. So it looks almost like it's in quadrant 1. So this would be vector A plus B. And so then what I want to do is I want to find the magnitude. I want to know how long it is, and I want to find the direction. I want to know where it points to. So first, since we have it in component form, let's go ahead and add those together. So vector A plus B is going to be 2, comma 14, and that simply just comes from adding the x's and adding the y's. And then recall, the magnitude of a vector, if we have the magnitude of a vector, the magnitude squared is going to equal the x component squared plus the y component squared. So in this case, the 2 squared is 4, 14 squared is 196, so that gives us 200. So the magnitude of a plus b squared equals 200. Remember, the 2 bars mean magnitude, how long it is. I'll take the square root, so the magnitude of a plus b is equal to the square root of 200, or 10 radical 2 units long, whatever the unit would be. So that's the magnitude. And that kind of makes sense. 14, this was 9. It's definitely longer than that. So 10 radical 2 doesn't seem that crazy off. So the direction is going to be the angle here, the angle theta. So it appears it is in quadrant 1 because it's over 2 up 14. And remember, the reference angle for this, the reference angle is the inverse tangent of the y over the x. So I'd be looking for what's the inverse tangent of 14 over 2. So when I do the inverse tan of 14 over 2 or the inverse tan of 7, I get 81.9 degrees. Now, since this angle is in quadrant 1, this is my direction. Just like before in section 1 when we did different ones that were in different parts, sometimes you have to add or subtract from 360 or add 180 or subtract from 180, just depending on what quadrant it's in. This one's in quadrant 1, so nothing too crazy about this. So our final one, this one we have 3 vectors, so we're going to try to put this together, these 3 vectors using a little trigonometry. The problem with these vectors are we don't have it in component form. We have it with angles and things like that. Now remember, we said if you have an angle and a magnitude, then the vector can always be written as the magnitude times the cosine of theta times the magnitude times the sine of theta. This was the 2 component form when you had an angle, like our 150 here, and a magnitude of 11.43. Now some of the other ones you can do with just kind of common sense, but if you have it, you can always do this. So let's call this vector A. So vector A is 10, 0. I don't really have to do any trig for that because it's over 10 and doesn't go up and down. Let's call this vector B, the one that's going straight down. Well, it would also have a pretty simple component because it wouldn't go left to right, but it would go down 10. So this would be the vector 0, -10. Now the last one is where we'd have to use our trig formulas to find its component form. So the magnitude of this vector is going to be 11.43 times the cosine of 150, comma 11.43 times the sine of 150. So this will give me my 2 parts of this vector. Let's call it vector C. So when I put these in, I am going to get negative 9.90. It's negative 9.898. So if we round it to 2 decimals, negative 9.90 and 5.72. So now when I'm adding all these together, when I'm adding vectors A plus B plus C, for vector A plus B plus C, for the x part, we're going to take 10 plus 0 plus negative 9.90. So that is going to give us positive 0.10. And for the y part, we'll take 5.72 plus 0 plus a negative 10, which is going to give us negative 4.28. So this is going to be my new vector. This is going to be the vector of all these added together. So this vector here is going to point, it's slightly to the right and it's down about 4. So this is my sum vector. This orange vector is the vector a plus b plus c. So if you can imagine these three vectors pulling on an object, then the object is actually going to travel along this orange path because that's the result of these three vectors working together. So we can also figure out the magnitude of this. So the magnitude of vector a plus b plus c is simply, that squared is going to equal 0.1 squared plus negative 4.28 squared. So 0.1 times 0.1 plus 0.428 times 428 is going to give me 18.33. And so the magnitude of that, a plus b plus c, is going to equal the square root of 18.33, which gives me 4.281. So it's really, really close to our sum vector, because remember, our sum vector was negative 4.28. It's really, really close to that. The reason it is because it's pretty steeply angled. As when we look for our direction is going to be this angle all the way around there. We know the reference angle to this is going to be the inverse tangent of negative 4.28 over 0.1. And so we'll put this in the calculator, and I know that I'm going to get a negative number, but I don't care about that because remember the reference angle is always going to be positive. So when I put this in the calculator, I'm getting negative 88.7, but we know that's not the reference angle. So if the reference angle is going to be 88.7, now we just have to figure out how do we find the actual angle. Well, since we know all the way around in quadrant 4, all the way around is 360 degrees, and we really just want to back up to get to this orange angle, our actual direction is going to be 360 minus 88.7, which is going to give us 271.3. So that's the angle that this sum vector is pointing at. So remember, when you're finding the direction, it really does matter what quadrant you're in. If you're in quadrant 4, it's 360 minus. If you're in quadrant 3, it's 180 plus. If you're in quadrant 2, it's 180 minus. So each quadrant has a little different way where you find its direction. So hopefully this was not too bad. If you have questions, obviously, please let me know.